So hello student, in this video we are talking about more of matrices. So we have more of equations involving matrices. We have one there. So how would we solve that? It is a very light one, so we can say solution, so we have a 3 into 1 plus x y minus open brackets x 1 minus 2y. Yeah, it is a good thing to recopy the question such that you can work with something accurate rather than going direct. So we see scalar multiplication, which we've done, and see that the scalar multiplies each component of the matrix. So we go for scalar multiplication. 3 times 1 is 3 plus 3x, then 3 times y is a 3y, then minus open brackets, I have an x into 1 minus 2y. This will equal to a 5, 9. We've done the subtraction of matrices. We do subtract corresponding components. So I have 3 plus 3x, then minus x, then I have 3y. Allow me bring the y direct, minus 2y plus 1. This goes here as a plus, then this will equal to a 5 with 9, a 5 with 9. So we simplify slowly. I have 3 plus 2x, and then this is going to be 5y plus 1. So this will equal to a 5 with 9. So what we do is we equate corresponding components. In other words, we equate components in similar positions, equate corresponding components. So I have 3 plus 2x is equal to a 5. The 3 crosses equal signs. It becomes negative, such that my 2x is equal to a 5 minus 3, such that my 2x is equal to a 2. Divide by 2, divide through by 2. And we agree that we are not just cancelling, but we are reducing by a common factor 2. Once, 2 once, my x is equal to a beautiful 1. So apply a bit of economics such that I have here a 5y plus 1 is equal to a 9. It goes the other side, such that I have a 5 something here that we need to rectify. This is minus. The minus affects 1 to make it negative 1, to make it negative 1, such that it's going to be 5y, minus 1. So 5y minus 1 is equal to 9. We take the one the other side, so this is 5y is equal to 9 plus 1. 5y is equal to a 10. Divide through by 5y is equal to a 10 out of 5. My y is equal to a beautiful 2. So yeah, it is as simple as that. This is a minus. Yeah, it is such a beautiful one. So let's go to, so we are on the determinant of a matrix. What is determinant of a matrix? If I have an arbitrary matrix Z, yes, Z, an arbitrary matrix Z, which is A, B, C, D, this diagonal here moving in my right hand side, moving to the right, is what we call the major diagonal. And then this one moving to my left, since it is moving to the left and the left is usually weaker, this is the minor D, the minor diagonal. The determinant of a matrix Z is abbreviated as det. So det Z, or determinant of Z, is a difference in the product of elements in the major diagonal A times D minus the product of elements in the minor diagonal C times B. In other words, it is simply AD minus CB. If we can get a simple example here, a very fine example, if you are told to find the determinant, the det of matrix Q, given that matrix Q is equal to 1, 2, then this is maybe 1, then this is going to be a 3. The determinant of Q will equal to a product of elements in the major diagonal 1 times 3 minus the product of elements, their multiplication 2 by 1, such that I have 3 minus 2, meaning that Q is 1. Yeah, let's look at the adjoint of a matrix. Yeah, so for the adjoint of a matrix, the adjoint of the matrix is the same as the adjunct. If I still use arbitrary matrix Z, yeah, as A, B, C, D, the adjoint of Z is these elements in the major diagonal, they run away from their positions. These ones in the elements in the major diagonal shift from their positions. Minor diagonal, they change the signs. In other words, my Z, it's adjoint. I can abbreviate it as ADG, adjoint of Z, change of positions, DA, change of signs, negative C, negative B. If they were negative, they become positives, and if one was positive, one was negative, the signs alternate. In other words, as an example here, if I had a matrix P, which is 1, -2, -3, 0, and then if I'm to produce the adjoint, the adjoint of matrix P, major diagonal we change position 0, 1, minor diagonal we change signs. As simple as that. Let's move to the inverse of a matrix. So if we are to move to the inverse of a matrix, how do we deal with the inverse of a matrix? The inverse of a matrix P is denoted by P power -1. That is the inverse P inverse. That is the inverse of P is P power -1. That is P, read as mathematical as P inverse. Such that how would we define P inverse? It is noted by that, and defined by P inverse is equal to 1 out of the date of P multiplied by the adjoint or the adjunct of P. We've looked at date and adjoint, so we are combining the two, such that if we take an example, find the inverse of matrix Z, find the inverse of matrix Z, that is equal to 2, -136. 2, -136, we need two things, computed date and adjoint. So we can have the date. So date Z is equal to a multiplication of elements in the major diagonal, 2 times 6, taking off the multiplication of elements in the minor diagonal, 3 times -1 is going to be 12 minus, okay, 12 minus 3, which is positive 15. Such that the adjoint of P, we've said on the adjoint elements in the major diagonal, they run away from their positions, 6, 2, and elements in the minor diagonal, they move from their positions, such that this goes to a elements in the major diagonal, they change their positions. In the minor diagonal, we are alternating signs, so this becomes -3, +1, such that the Z inverse will equal to 1 out of date. So this is 1 out of 15. Then I'm multiplying it, multiplied by the adjoint I've computed, 6, 1, -32, such that I multiply. So this is like scalar multiplication of each element by 15. Have 6 out of 15, -3 out of 15, 1 out of 15, then 2 out of 15. I can leave these guys as simplified fractions, minus computing to decimals, which will make me round off, such that I can have 6 out of 15 by 3 here, by 3 here. It is a 2 by 3, 5 by 3 once, by 3, 5. Don't just cancel. So it is going to be a 2 out of 5, a -1 out of 5, a 1 out of 15, and a 2 out of 15 as my Z inverse. Yeah, so we are going in the next video, we're going to make, I think, a shorter one for understanding how we solve simultaneous equations by matrix method.